This is lesson 21 of the A-level physics no-nonsense lessons, and this one is all about stationary and progressive waves. Now, we already heard last lesson about how we can make stationary waves if we have the superposition of two waves of the same frequency travelling in opposite directions so that the waves cross over. And where they cross over, they superposition. Where they superposition, we add together the displacements due to each of the waves. In certain positions, that will lead to larger amplitudes. That is to say, the maximum displacement of the resultant wave of those two progressive waves added together. The resultant amplitude will be larger, and in certain places, the resultant amplitude becomes zero. And we called those nodes and antinodes. So let's just pick up there then. And let's take the simplest example of a stationary wave. Let's take the example of a piece of string. So if I have, let's just make a title of this. Let's put stationary wave on a string. So stationary, and regular watchers will know that I often have problems spelling. Waves on strings. Let's go with that. So with stationary waves on a string, we could have a situation where we have a vibration that originates somewhere along the string and travels in both directions. It reflects off a barrier at each end, what we would call a boundary at each end, and then returns to the middle, and then crosses over past the middle and carries on in its direction. So let's say this is our piece of string of length unknown. There's a joke in there somewhere. And at each end, the string is fixed. Maybe this is a ukulele string, so one side is fixed to the bridge and the other side is fixed to the nut. Maybe it is a skipping rope and there's a child at each end of the string. It doesn't matter. But at each end of the string, the amplitude will be fixed at zero. So we can call each end of the string a node. And let's use a different colour for this. And let's label an N at this end and an N at this end here. They are nodes. Now we could have the string at some instant in time looking a bit like this. So at the edges, we've got an amplitude of zero, but in the middle, the amplitudes of the displacements of the two waves travelling in opposite directions happen to add up constructively, and we get this super crest. And at half a time period later, the string would be down there. It's not very well drawn. I should have another run up at this. Half a time period later, the string would look like this. And so in the middle, we have what is called the antinode. And there we go. Now this is the lowest wavelength that you are going to, the highest wavelength, the lowest frequency that you are going to get on this string. If you imagine we unwrapped this string, we unwrapped it, what we would have is, rather than the wave at the top bouncing back and going along the bottom, it would go like this, all the way to that position there. So imagine that we've taken, let's get the highlighter pen out, imagine that we have taken this part of the string here and unfurled it so it's here, just like that. Well, in that case, what we have is one wavelength in length from here, from this first node, all the way over to there. That is one complete wavelength. The pen stopped working partway along, so let's try that again. That is a length of one wavelength. Well, if that's a length of one wavelength, then the distance from one node to the next, so the distance between two adjacent nodes, is half a wavelength, just like that. So the wave has an up part and a down part. And we have the waves on this string such that as the waves travelling from left to right are telling the string to go up, the wave that's reflected as going from right to left is saying the same thing. In order for that to happen, we'd have to have half a wavelength between those two nodes, the bridge and the nut of our ukulele. Just like that. Now, of course, this is going to happen at a certain frequency, and the progressive waves that we're adding together to make this stationary wave would travel at a speed equal to the frequency of the stationary wave, same as the frequency of the progressive wave, multiplied by the wavelength of the progressive wave, which is half the distance between the nodes on a stationary wave. So I probably should put some words to that effect. We can say that the wavelength of progressive waves that are added to form a stationary wave. Remember, I write this because it forces me to slow down, and it gives you time to draw your own notes, write your own notes at the same time. So wavelength progressive waves that are added to form a stationary wave are twice the distance, so 2 times the distance between adjacent nodes. And we defined nodes last time, but just for completeness, let's put the definition of nodes and antinodes on this particular slide as well. So n equals node, and in brackets amplitude, and this is amplitude, I can't even read that, and this is the amplitude of the stationary wave, not the amplitude of the progressive waves. Amplitude of stat dot wave, I'm just abbreviating it, is equal to 0. The maximum displacement of the string is 0 at the nodes. The antinodes, label it like that, at the antinodes the maximum displacement, so the amplitude, is not equal to 0, it's equal to a maximum. So we can say, let's use a lowercase a for consistency. Amplitude is equal to maximum. Now this can be confusing for some students because, of course, with progressive waves the amplitude doesn't change along the wave. Well, of course, it wouldn't change if the wave wasn't spreading out, so the energy wasn't spreading out. We would consider the wave to have the same amplitude all the way along. At any instant in time, the displacement of the wave may be different, but the amplitude wouldn't. Let's just go back a few pages of notes to have a look at some basic wave properties. Maybe it was in the next one after that, where no, it wasn't. Where was these basic measuring waves? That was it. It was under measuring waves. We had the displacement on these graphs changing, but the amplitude was always the maximum displacement. These are progressive waves. We're now looking at stationary waves, and for stationary waves, the amplitude is different along the stationary wave. Any point on this string is oscillating. And in the way I've drawn it here, it's oscillating up and down. It's a transverse stationary wave because the wave energy would be being passed from left to right and from right to left. And this is interesting because the rate of transfer of energy from left to right is equal to the rate of transfer of energy from right to left. So the net transfer of energy is 0, one of the definitions of a stationary wave. But all of that's happening horizontally in the way I've drawn it. Perpendicular to that are the vibrations of the string, the oscillations of the string, the displacement of the string. And so the string is oscillating up and down, the string is oscillating perpendicular to the direction that the waves are travelling. And we can see that at the antinode, the string, the piece of string that's oscillating, is oscillating with greater amplitude than the piece of string that's oscillating near a node. And at a node, well, it's not oscillating at all. If we plotted a graph versus time of the displacement of a piece of this string, it would just look like one of those. In fact, it would look like the graph on the right, the displacement of that part of the string over time. It would look like a progressive wave in the diagram. But it's not. That's just because we're plotting it versus time. For it to be a progressive wave, the energy would have to be transmitted from one place to another. And that's not happening in this case. Okay, so we've got a stationary wave. We've seen what it looks like. Now let's see if we can understand the concept of harmonics. And there are different harmonics for these stationary waves. So I'm going to do a bunch of diagrams. Let's just label this harmonics. And I'm going to try and keep it so that we don't go over one page of notes per lesson. But there's quite a lot we can talk about with regards to harmonics. How much paper have we got? Yeah, we've got enough. Let's look at harmonics. And I'm going to do the first 4 harmonics. So let's leave a bit of space at the left. Let's say that that is the first harmonic. That is going to be the second harmonic. This is the third harmonic. Oops. This is the third harmonic. This is the fourth harmonic. There's my 4 pieces of string. I'm not sure if I mentioned this, so I will just mention it now. When you look at a stationary wave, what you see is at one instant in time the string is up there, and half a time period later the string is down there, then half a time period later the string is up there. And of course between each of those the string is smack bang in the middle. So it's the skipping rope going up and down. That's what we're talking about there. I'm not going to put that in the notes. Mainly because I think it's kind of covered in these notes here at the top right. Okay, so back to harmonics. We've got the n equals 1 harmonic. This is the one we've already seen. It's called the first harmonic. It's also called the fundamental mode. That's mode, M-O-D. I'll label that here, actually. Fundamental mode. And we've already met the fundamental mode. That's the one where the string, I'll use red for the string, stick with the convention. That's the one where the string oscillates. Come on, start from the beginning. That's the one where the string oscillates up. Try again. Oscillates up to the end there, and then down the other side. It swings between those two, and we have node, antinode in the middle, node. Now the second harmonic, n equals 2, the second harmonic, this looks slightly different, because now we have still got a node at each side. We are taking the situation where we have 2 boundaries that are fixed, but we also have a node in the middle, and therefore we would have antinodes at the points halfway between the nodes. So an antinode here and an antinode there. So now the string appears to go from the left-hand node up to where the amplitude will be maximum, down to the node in the middle, down to there, and back to here. And that's the way the string would look at one instant in time. Then half a time period later, it would be doing the opposite. Now clearly there we have a different frequency and a different wavelength. But the wave speed is the same. This is important. The wave speed is the progressive speed of the waves on this string. And the waves on this string, their speed depends on the tension of the string, it depends on the mass per unit length of the string. We'll talk all about the speed of the waves on a string later on. There's a whole section on it coming up. but we'll leave that for now. Where was I going with that? Oh, yes. So the speed of the waves on this string, the speed of the progressive waves on this string, don't depend on the wavelength. They don't depend on the frequency, which means that if I halve the wavelength, which is what I've done in this case, I've doubled the frequency. So if we say that this is a frequency equal to f0, the fundamental frequency, and we say that the wavelength is equal to lambda 0, the fundamental wavelength, then in this case, in fact, let's not call them zeros, let's call them ones, because, oh, that's annoying, I have to undo it all the way back to there. Let's call it 1, like that, because it's the n equals 1 mode, so let's use the subscript 1. Then in this case, the frequency will have to be double that, so f2 is actually equal to twice f1, and lambda, which is lambda 2, is equal to half lambda 1. And we could do the same thing for the third harmonic, and we will. So n equals 3, the third harmonic. There is another name for these, by the way, which I'll come to at the end, if I remember. And in this case, we have a node at both ends. But now, rather than having one node in the middle, we have two nodes in the middle. And then we have antinodes between the nodes. So how do I form these harmonics? Well, I get the string shaking around, oscillating with a certain frequency. If I double that frequency, then I get the second node that's appearing. And if I increase the frequency again, that's badly drawn, I can get the third harmonic. But by how much? Well, that's what we're going to work out. So at one instant in time, it would look like that, and then half a time period later, it would look like that, and oscillate between those two. Now, what's going on here? Well, the frequency is going to be, or f3 we could say, is going to be equal to thrice f1. It's going to be thrice f1. And the wavelength, lambda, is going to be equal, this is lambda 3, is going to be equal to a third of lambda 1. Just like that. Now you can see that the distance between nodes is a third of what it was, and the wavelength is twice the distance between adjacent nodes, and therefore it has to have a third of the wavelength of the first harmonic, the fundamental mode. And we could have a look at n equals 4, the fourth harmonic as well. Now, I promised I would tell you another name for these, so let's do that. How do you spell fourth? Has it got a U in it? I'm putting a U in it. It's probably wrong. Might be like fifth, which has an F halfway through it for no reason. Spelling's hard. Harmonic. So here we go for our fourth harmonic, also called the third overtone. Oh no, that's complicated. I know. It doesn't get any easier. So here's some nodes, and we're going to have antinodes in between them. I'm not going to draw the antinodes because it's going to start getting a bit cluttered, but they're there. And we have that at one instant in time, and then half a time period. Try again. Half a time period later, it's going to look like that, and oscillate between the two. So, yes, we can call the fundamental mode the zeroth overtone if we were feeling a bit perverse. We could call the second harmonic the first overtone, because that's what it is. We could call the third harmonic the second overtone. Fourth harmonic is the third overtone. Now, the term overtone isn't really used in A-levels anymore. If you're a musician, then you may well have heard, especially if you're a guitarist, a contemporary guitarist, then you may very well have heard the term overtone. This is what overtones refer to. It used to be on the A-level course, but now it's not. So let's put all those ideas together then and see if we can come up with a general rule for the wavelength of each harmonic, depending on its harmonic number. And remember, in each of these cases, the string was the same length. So let's call the length of the string L. And let's make a little note of that. L equals the length of string. And I also need to include notes about the wave speed. I mentioned it, but I didn't actually mention it. I mentioned it, sorry, but I didn't actually write it down. Otherwise, you won't have it in your notes. So C equals F lambda, that's still true. And C, which is the progressive wave speed, progressive, remember there are two progressive waves which are interfering to form this stationary wave. So C, which is the progressive wave speed, does not depend on frequency or lambda. I'm not saying it's constant, because it does depend on the mass per unit length of the string, and it does depend on the tension of the string. But it doesn't depend on anything else. So I'm not going to call it constant, but I'm just going to say it does not depend on them. So we could say in general that the frequency of the nth harmonic, is going to be equal to n times the frequency of the first harmonic, the fundamental frequency. And we can say that the wavelength of the nth harmonic is equal to the wavelength of the fundamental mode divided by n. And we can go a step further as well, because we know that the wavelength of the fundamental mode, or the first harmonic, is twice L. So we could say that this is equal to 2L divided by n. Just like that. And we can go a step further as well, because we can say that C, which is a constant in this case because the strings have exactly the same tension and mass per unit length, which is equal to the frequency for a given, let's just try and get this right, the frequency for a given harmonic multiplied by the wavelength for a given harmonic is equal to, and you'll see the n's will cancel if I just plug these in, n1 f1 multiplied by 2L over n. So you can see that the wave speed does not depend on the harmonic number. But we can take it back a step and we could express the frequency of the nth harmonic in terms of the wave speed and in terms of n and L, because C equals F lambda, F equals C over lambda, so F equals 1 over lambda, so F equals n over 2L multiplied by C. That's the frequency of the nth harmonic is equal to the harmonic number divided by 2L multiplied by the speed of the progressive wave that travels along that string. Okay. So, right, that is one example of a harmonic, but it's not the only a harmonic series, but that's not the only harmonic series we can get. And for the next couple of minutes, I'm just going to give you another example. So this is waves on a string, and I should probably include that somewhere. I might have to just grab this and move it down. If you're making notes at home and trying to make them look exactly like what's in front of you here, you're about to get very, very grumpy. So let's try and... Oh, that didn't quite work, did it? Can I grab that and move it down? Oh, nearly all of it. Let's grab it and move it down to there. And I'll just redraw that curly bracket. Right. I did say it was no nonsense. Sort of. Curly bracket. Bracket there, right. So let's label this waves on a string. Oh, the F has not copied over either. Oh, maybe I should edit this bit out. I don't like editing things. Let's go back to there. Go back to black. We'll put the F in here. Right. This is waves on a string. So let's label it as waves on string, but not just that, it's got two fixed boundaries. But there are other ways of forming stationary waves where we don't have two fixed boundaries. We could, for example, have waves in a pipe, where one side of the pipe is closed and the other side of the pipe is open. So let's have waves in a pipe, and we'll just rattle through this very quickly. Waves in a pipe, and this is one fixed boundary, one open or free. You can call it a free boundary as well. Boundary. So what would this look like? And this might be a musical instrument such as a pipe organ, I guess, or something like that. Pan flutes, maybe. I don't know how they work. I'm not a flautist, but here we go. We have our pipe, and I will try and draw a bunch of these orders in this pipe. There's one pipe, there's another pipe, and these are all the same length pipes. There's another pipe, and should we do 4? Let's do 4. There's another pipe, and that probably takes us down to the bottom of this page of notes. Yes, it does. And we're going to label them. This is n equals 1, the fundamental mode. This is n equals 2, the first overtone. This is n equals 3, the second overtone. This is n equals 4, the third overtone, the fourth harmonic. And we need to make it bound. So we're going to fix this side, like this. And then somehow we're going to cause the air inside this pipe to vibrate. And what can we get happen? Well, we can get the pressure in the air going from being like this, fixed at one end but open at the other. And what we've actually got there is a node at this end here and an antinode at the end. Then we could have, instead of a node and an antinode like that, it could be, let's try and draw this right, going up like this and down to there. Down like this and up to there. So in that case, it's an antinode at the end, it's an antinode at this end, it's a node, and it's a node. Now the node spacing and antinode spacing should all be the same for a particular harmonic. And we can do it again. So we can go, let's say, up, up, down, up. Ah, missed. And down, down. Ah, that's very badly drawn, because look, the wavelength appears to be changing, but you can do a better job yourself. So remember, the spacings for all this should be the same, but look how badly drawn that is. The antinodes at the right are clearly closer together than the antinodes at the left, and it should not be like that. But you get the idea. We'll analyse this in a second. And then the last one, the fourth harmonic. Yikes, right, up, down, up, down. Here we go. Up, down, up, down. Up, down, up, down like that, and we can label node, 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 and we've got, that's a funny N, and we've got the antinodes as well, which I might as well try and put in here. Now in each time we're adding one node and one antinode to our series each time. The length of the pipe, what colour did I use? Green. The length of the pipe we can keep with L, so let's label the length of the pipe L. And if we know the distance between a node and the adjacent node is half a wavelength, then the distance between a node and the antinode is a quarter of the wavelength. Wonder whether we should put that in the notes somewhere, whether I put it in there. No, I'll put it in here. So we could say here that the frequency in this case is our fundamental frequency, F1, fine, and our wavelength is our fundamental wavelength, lambda1, fine. This is different to before because it's a different situation. And we could write that in terms of L as well if we want to. So if we go back to this example, we could say that that is equal to 2L. And this one is equal to 2 over 2L. This one here is equal to, what is it equal to? That's 2 over 1, 2 over 2, 2 over 3L. This one here is equal to 2 over 4L. So we can do the same thing with this. We can say that that is equal to, and this time it's obviously going to be 4L. It's different to last time. Okay, it's a quarter of a wavelength between the node and the adjacent antinode. So 4L is going to be one wavelength. Now what's going on in this situation? Well, in this situation, F, which is now F2, how does that relate to frequency? We'll figure it out in a sec. And wavelength is equal to the wavelength 2, which is equal to what? Well, here I can fit 3/4 of a wave onto the length of the tube. So L is going to equal 3/4 of a wavelength. Or the wavelength is 4/3 of L. It's just the reciprocal. So let's put 4 over 3 L, just like that. We'll worry about what the frequency is doing in a second. And this one here, frequency is equal to F3. We'll worry about what the frequency is doing in a second. And the wavelength is equal to 4 over 5 now. Look, we've got one full wave and then a quarter of the wave. So it's 5/4 of a wavelength is L. L is 5/4 of a wavelength. It's 1 plus 1/4, so 5/4. So that's going to be 4 over 5 L is equal to lambda. And then the same thing here, frequency, and you probably spotted the sequence already for the wavelength, and we're going to use that to figure out what's going on with the frequencies. So lambda 4 is going to be 4 over 5, 6, 7 L, like that. And the wave speed is the same in each case. It has to be the same in each case. Oh, I did it in terms of L. I didn't do it in terms of wavelength. Oh, what a fool! I should have done that before I put those L's in. Should I do another copy and paste job? Should I make it so that everyone gets even more irritated with me? Yes, I will. I didn't get into this job to make friends. So let's try and make your notes a bit clearer. Move that over. Oops. Right. Another run up at it. There we go. Move that over there. Let's fill in the lambda parts. Come on. Come on. Fine. So what's happening with lambda here is... Oh, I shouldn't have moved that one. That is just 4L. I shouldn't have moved that one. But then I want to write them in terms of lambda 1, don't I? So, pen, here we go. So we're going to put what the factor is in terms of lambda 1. So what's happening to it? Right, so the wavelength is 1/3 of what it was before. Okay, you can see that because that bit there, the distance between a node and an antinode, is now 1/3 of the total pipe. There's now 3 of them, if it was drawn properly. So that's 1/3 of that wavelength. And I could do the same thing with this one. It's now 1/5 of lambda 1. Now we're rolling. It's 1/7 of lambda 1. Drawing the diagrams can really, really help. So what's going on with the frequencies then? Well, if the wavelength has gone down by a factor of 3, the frequency must have gone up by a factor of 3, by a factor of 5, and by a factor of 7. So that, when you multiply them together, you get the same wave speed. Now, what else did I say? Oh, I was using a general equation. So let's see if we can come up with a general relationship for lambda. What we could say is that lambda n is going to be equal to, and you can see these numbers yourselves, 4 over some other number which we're going to figure out in a second, multiplied by L. And what is that number? Well, for the first harmonic it's 1, for the next harmonic it's 3, for the next harmonic it's 5, and so on. So it's going to be n times 2 minus 1. 2n minus 1. Let's just test it. When n equals 1, 2n is 2, minus 1 is 1, 4 over 1 is 4, 4l, which is what we get. Take the highlighter pen out while we rattle through the next bunch. So if we look where n equals 2, if n equals 2, 2n is equal to 4, 4 minus 1 is 3, 4 over 3, 4 over 3, that works. And we can do the same thing for, let's just test the last one, n equals 4. So 2 times 4 is 8, minus 1 is 7, 4 over 7, 4 over 7. So now we have our harmonic series for our tube, which is fixed at one end. And we could write that in L equals instead. I'm going to leave it like that. Notice it is different. Before we had lambda n is equal to 2L over n. Now we've got lambda n is equal to 4 over 2n minus 1 all times L. It is different. Our speed would be the same in each case, so our speed is equal to frequency n multiplied by 4L over 2n minus 1. And so if we wanted to calculate what the frequency was for the nth harmonic, it is just going to be 2n minus 1 over all over 4, I'll write it with the brackets even though it's not necessary, C divided by L. That's what it would be. And I think that's really all we need to say now. We could have a look at when the pipe is open at both ends, but what you'll find when the pipe is open at both ends is it looks exactly the same as this series here. Rather than having a antinode in the middle and a node at each side for the first harmonic, for the fundamental mode, it's a node in the middle and an antinode at each side. And for the second harmonic, it would be just swap the nodes and antinodes. And for the third harmonic, just swap the nodes and antinodes. So when you've got a pipe which is open at both ends, you get the same harmonic series as when you have a pipe that's closed at both ends, or a string that's bound at both ends, two fixed boundaries. The interesting one is what happens when it's got one fixed boundary and one that is not fixed. So let's just put some highlighting on some of these. Let's do it like this. Highlighting on some of these formulas. Can I do it as a box? Will it let me do a box? Yes, it will. Just so that we can follow what's going on. There's our harmonic series there. Oops. There's our harmonic series there. And let's leave it at that. So next lesson we're going to look at more about stationary waves on strings and start having a look at the significance of the speed. What is the speed? How do we calculate the speed? That's going to be our next lesson. This was quite a dense lesson. There was an awful lot in it, but hopefully you found this useful. We also need to talk about phase differences along the stationary wave, and we'll do that next lesson. So I hope you'll join me then.